Hello and welcome. We are jumping into our third video of the week with the solid principles. Now, this is probably one of my favorite topics, like across the entire course. We're going to break it up over two videos because each letter in the word solid stands for a different design principle, and that can be a lot in one video. So video one is going to focus on S, O, and L. So we can see that there's three principles listed right here, and then we will do I and D in the next video. We're going to talk a little bit about understanding what the principle means, how to spot when you're violating the principle, and possible ways of fixing them as well. It really is one of my favorite topics because it really helps us just make beautiful code. All right, so let's start by just discussing what solid actually is. It came from this design philosophy. Well, basically it is a design philosophy for better code. So the acronym basically gives us 5 different design principles that's going to allow us to write code that will be maintainable, scalable, understandable, and incredibly testable. And all of these things help build credibility and trust within our team, within our code, and within like our clients, within our customers. So here's each of the acronym letters. We have the single responsibility principle, the open-close principle, Liskov substitution principle, interface segregation, and the dependency inversion principle. And I promise at some point these will feel like second nature to you. Right now you might be reading them all and going, oh great, another 5 things to memorize. But hopefully I can sort of motivate the names for each of them, and that will help you sort of solidify remembering which ones are which and what we do with them. I promise it's not that bad. So these were introduced by Robert C. Martin. Pretty sure that he's like the C guy. I think I have a textbook by him. It's possible. Apparently people called him Uncle Bob. He was popularized in the early 2000s in many object-oriented programming circles. And people use these in other languages, not just in Java, right? So these are object-oriented programming principles. These are not language-specific principles. Also, they're guidelines, not laws. So just like everything else in this course, they're tools that we want to add to our toolbox. This is not like if you have a violation, you automatically have written terrible code. This is going to be like if you have a violation, you should be asking yourself, is it necessary? And is there a better way to solve the problem? Okay, so let's jump in with the first. We have S, which is the single responsibility principle. Now, the main definition basically reads, a class should have one reason to change. What we see here is we see that we have a Swiss Army knife with something like 700 million gazillion utilities on it. And the problem is we can't actually find anything in here if we needed to use one of them. We also can't really use any of them that well because like other sharp tools might get in the way while we're trying to use knives and scissors and things. And we also like, how are you going to carry this? Like, how are you going to fit this in your pocket, right? So just because we could make a Swiss Army knife that would be this big, it doesn't really mean that we should, right? The single responsibility principle is that each unit of your code, each class or each method should have one reason to change, a single responsibility. So perhaps this Swiss Army knife gets turned into 4 to 10 Swiss Army knives, one for scissors of different sizes, one for knives, one for clippers, one for bottle openers, and one for screwdriver bits, right? We can sort of see how we could break this down while still maintaining this idea of wanting it to have multifunction. We don't want to have one Swiss Army knife per responsibility, but we could sort of break this down a little bit differently. Let's take a look at some code here. I have an area calculator. This area calculator has an array list of shapes. I didn't put the shape class in here, but we can assume that this code is written in a way that will make sense. This shape code might be on the next slide. I can't remember now, but what we can see is we have an array list of shapes. We can assume that right here the list is being filled by a data file, so it's a full list of shapes. If you try to do print total sum, it will get the sum of all of the shapes and it will print them out. If there's squares, it's going to use this formula, and if it's circles, they're going to use this formula. Now, just like which one was it? Ooh, my brain is slowly falling apart. Did I give it an acronym? May not have given it a direct acronym other than maybe separation of concerns, right? SOC. Anytime you hear the keyword and in describing a piece of code, there's a good chance it should be separated out into different pieces. Again, not always, but within reason. So if we look here, if somebody asked me, if I asked you, what do you think the area calculator does? My hope would be that you would say it calculates the area. If I were to then describe for you what this area calculator does, it fills a list of shapes and it calculates their area and it prints it out. So we can see that we got this and business going on. This has too many responsibilities, especially given that the name is not called area calculator and principal and printer or area shape getter, calculator, printer, formatter, who knows, right? We can see that this is going to be too many responsibilities. So what can we do instead? We can separate these out. We've left the getting the list of files in over here, but that could absolutely also be separated out and instead be passed in through the parameters of the constructor, but we'll just ignore that one for right now. One violation at a time is enough. We can see that we now have our area calculator that, given that list of shapes, does its calculation. And then over here on this side, we have the sum outputter, which has an area calculator internal to it. So it has a calculator, and then we can output to console. Maybe we output JSON format or different types of formatting options. Now, keep in mind that I am highlighting the code that I want you to pay attention to, which is the fact that we've now separated a printer and calculator into two separate classes. There are other things that are wrong with this code that I am purposefully ignoring right now. We will look at them in future violations and in other scenarios. So for right now, we're really just focusing in on the fact that we had one class that really should have been turned into two. And the way in which we did that meant that we ended up with a class over here that had that made use of composition, right? The has-a relationship. So a sum outputter has an area calculator. And that makes sense because if you actually think about a calculator, like an actual physical calculator, what is it? Well, it has number buttons and it has formula processing and it has a display. So it actually makes a lot of sense for the calculator, the item, to be considered separate from the display pieces and the calculation pieces. So we could take this even one step further if we wanted, if it was a more complicated example perhaps, and really have like a shell that is our calculator, and then we would have a display formatter class and a formula calculation class or whatever, a number calculation class. I have no good name, but we can see how composition would allow us to sort of break this down further. What often happens with our code is it mimics how we think about things in real life, and that brings us back to this idea of cognitive inertia. Because in real life, when you see a calculator, you don't think about it being this like all of its different parts. You're just thinking of it being the sum of its parts. It's a calculator. It calculates things. It displays things. It allows you to try different numbers of things. Some let you play games, whatever it might be, right? We don't really think about it in the sum of each of those individual components that make it into a calculator. So our initial example here is indeed how we might think about it in the real world. But if we want to think about it a bit more like a computer, we'll realize that it should be broken down because each class should only have a single responsibility. All right, our next principle is the O, or open-close principle. This is one of my favorites. So weird to say, but it is true. The official term, or the official definition rather, is open to extension, closed to modification. But I'm not sure that that makes a ton of sense without analogies and examples. So I feel like this is starting to be like more of a dated reference, but like Edward Scissorhands, he has scissors for hands, right? That's like his shtick, if you've ever like seen the movie. Anyway, he has scissors for hands. They're welded to his hands. If he wants to like eat an ice cream, he can't. Like he can't hold it. Somebody's gonna have to feed it to him, poor guy. You'd have to cut his hands off and like sew the ice cream hands, I guess, onto him. So he's so sad because he can't do anything except use scissors, and he'd have to have surgery if he wanted to to make changes here, right? So what we can see here is that he is not open for extension. We cannot easily extend the fact that we have pointy scissors on our hand, and he's not closed to modification. He's open to modification. We would have to cut off his hands. We'd have to fully modify his body just to change out this part. But thank goodness for evolution, right? We have hands. We have hands with digits on them. So over here is Edward Normal Hands, who exists in the real world. And Edward Normal Hands is now open to extension because he has a hand here. He can hold a pair of scissors. He can hold an ice cream cone, right? He doesn't have to have surgery and like recovery time to make those changes. So we want to be open to extension, so plug and play, closed to modification. We don't want to have surgery. All right. Here is a violation of the open-close principle. We did see a similar violation in my single responsibility principle example with the different shapes. So if we want to be able to use a tool in an array list of tools, we basically would go through every single tool in our toolbox, and we would say if it's a hammer, we're going to print out bang, bang, and if it's a screwdriver, twist, twist, and if it's scissors, cut, cut, right? And we can sort of see that each of these is going to have its own printout of what it might do. Something like this could live maybe in like the tool class or in like a used tool utility class. And when you pass in the array list of tools, you want to be able to go through, and depending on which one it is, you're going to do something different. Okay, this is a violation. Anytime you have a switch statement, anytime you have if, else, or more else ifs, right? Like anytime you have those like multiple levels, you should be stopping and asking yourself, could I do this differently? This becomes very tricky on the front end. It becomes a really interesting discussion with like hash maps and like how can we solve these problems and enumerators and iterators. But we'll get into some of those fancier sort of design patterns later. So right now, we see this, we see that we have multiple if statements, and we say, no, that is a violation. So what can we do instead? Well, we can absorb this idea of tool sound. So we can do this in a few different ways. When we look at this, it's obvious that we have a hammer class, a screwdriver class, and a scissors class. Each of these needs to implement a tool sound method. How do we enforce that? Well, tool is going to be an interface that's going to enforce tool sound. Oh, I thought I had a picture of that, but I don't. Tool is an interface, and so each of those hammer, screwdriver, and scissors would implement our interface, and then each one could have a tool sound function that would print out or that would return bang, bang, twist, twist, cut, cut. And then this use tool function can now just say for each tool, get the tool sound, and it's much cleaner code. Everybody owns their own sounds that they need to make, and now this function can easily swap them out. What does it mean that this is open for extension and closed for modification, you may ask? It is open for extension, meaning we can make additional tool types, but we wouldn't need to change this class. That is what we're aiming for. So now if I get another tool, I get a saw, and I want to also implement the tool interface for the saw and implement the tool being added to my toolbox somewhere else in the code, this method does not need to be touched. We are open for extension as a code base, and this method is closed for modification. It does not need to change just because we added a new class. That is the name of the game. All right, the last one that we're covering today is the Liskov Substitution principle, LSP. Basically, the gist of this one, people find this one the trickiest because the name doesn't immediately instill an understanding of what this principle is. It actually does with the word substitution in it, but people kind of mess with it a little bit and struggle a little. So it means every subclass should behave like a parent class. So what we see here is if it looks like a duck, quacks like a duck, but needs batteries, you probably have the wrong abstraction. So if we have a duck superclass, and underneath the duck superclass, we have hook-billed ducks, and that's literally the only duck name that I know. Green ducks, I don't know. It's a poor choice for me, but this is the standard choice. And then we also have bath time ducks, rubber ducks, right? A robot duck. And those all fall underneath this superclass of duck because they're a type of duck. The problem is you need to turn a robot duck on Whereas by default, that is going to be always on if it's an alive duck, right? So this is going to actually prove that we're using the wrong abstraction. We shouldn't be using a superclass parent relationship because this subclass is not going to behave like the superclass. A quick aside, this is actually named after Barbara Liskov, a woman in computer science. She was actually the first woman in the US to earn a PhD in computer science. And her thesis was actually on artificial intelligence back in the day, way before it was trendy. Barbara's super cool, so it was really important to me that I included some information about her. I heard her speak actually at a conference, which was so cool and so inspiring. Did she really name a principal after herself? She actually didn't. She never, ever, ever coined that term. Robert C. Martin, the individual who I originally mentioned was in charge of creating this system, he was actually in charge of naming it because it's his solid principles. And he actually named it after her in honor of her work on behavioral subtyping and on robust interface design. So it's not like, oh, she was being self-centered or anything like that. Robert C. Martin actually went and named it after her in her honor, which is pretty cool. She's also a Turing Award winner. So back in 2008, she won the award for pioneering work in programming languages and system design. She actually created the CLU language, which is so cool. She's like, I'm fangirling a little, like she's my hero. She's absolutely my hero. After she spoke at the conference I was at, I had sent her an email and I was like, you're famous. I love you. You're so cool. And she responded. And so now I have that email printed out on my wall at home because she responded, and that's so cool. You can tell who's an academic because their heroes are like random researchers. But it is pretty neat to sort of know that that kind of history isn't really like 100 years ago, right? We're not biology, we're not chemistry. Computer science history is today. These people are still alive. Anyway, back to the principle itself. Here we can see we have a file reader up here that reads a file. Cool file contents, no problem. Here we're going to have a secure file reader that extends this original file reader, and we have to override this method because this file reader just returned like sort of a base class information, but this one over here is going to throw an exception because it's a secure file reader and you can't just pass in the path and have access to reading the file. So it says, access denied. Coming back to over here, this is in our main class down here. Here we have a file reader because it's the superclass, and we can equal a new secure file reader, right? It can be of subtype secure file reader. Now, if we go and we try reader.read file, and we do secret.txt, because presumably this is going to read a file of some kind, right? We know that our read file throws an IO exception. So our statically typed variable right here is going to have the compiler require that this is a checked exception because it throws an IO exception, right? So your compiler is going to tell you need a try catch. So you're like, all right, okay, try catch before you use the read file method. So you do that. This says throws IO exception. So that's what it is you have to catch here. You try reader.read file secret.txt, but thanks to dynamic polymorphism, this read file is actually going to go into here, right here, read file, string path, throws exception, security exception. It will throw that security exception. We're not catching it. We can't handle it. This subtype of secure file reader that extends file reader is not easily substitutable. It does not behave like its superclass. This is a Liskov substitution principle violation. It doesn't only come up in the inheritance world, but it comes up a lot in the inheritance world. There are other ways to find yourself in this situation, but this is probably the most clear-cut example that I could show you. Now, how are we going to fix it? Like I said, it isn't just about inheritance. It's behavioral compatibility, right? So we have different ways that we can fix it. Fix number one is to make sure that they're both throwing the same kind of exception, right? Throw an IO exception instead. If we use an IO exception or even just a subclass of an IO exception, we can stay within that expected contract. So now we can still override it. And instead of throwing a security exception, we can throw a new IO exception. And this will allow us to behave just like our parent. The other fix is to wrap that unexpected exception. So here, instead, we're still going to throw that IO exception. If we have a try catch still, right? Internal to secure file reader, pardon me. And if you don't have permission, you're going to throw that security exception because it's an access denied. But we catch it internal to the read file and throw a new IO exception with the security violation that was caught. So if you have, let's say, some kind of logger where you still want to log a security exception being thrown, so you don't just want to do away with it completely, you don't have to. There are other ways to solve this problem. You can use a try-catch internal. As long as we're catching and throwing two different error types, this absolutely would work. We have one more example here because that one was an example using inheritance where inheritance made sense, but we needed to adjust how we were implementing this inheritance. Here we have a little bit of a different example. So here in our rectangle class has a width and a height. We can set our width, set our height, and our area is multiplying them together. Whereas in a square class, that's not actually the case, right? If we set width, it's going to actually change both. Or if we set height, it's going to actually change both. So we do override these to use these two over here because in a square, those have to be the same. Many people will tell you a square is a type of rectangle, and I just said is a. Square is a type of rectangle. So somebody might want to write code like this, right? But now, if we try to have a rectangle R equal new square, which will be totally fine compile-wise, r.setWidth will bring us into here and change both to 5, and then r.setHeight will change both to 10, and system.out.println.getArea not going to work. It'll work, but we'll get 50 we'll get 100 as opposed to potentially 50. Now, based on the contract that's set at compile time, the rectangle is kind of expecting it just by reading the code, right? Not running it, obviously, but by reading the code, we might expect it to be 50. But once we realize that dynamically it becomes a square, this will actually give us 100. And this r.setWidth 5 does absolutely nothing. This is a contract violation, right? We're expecting it to behave like a rectangle. It does not. We have the wrong abstraction. So how do we solve this problem? Well, rather than an extension relationship, what we need is an interface relationship. So fix 3 is, so we have do I have both here? Yes, good. Just making sure. So the next fix that I have for solving this problem is composition over inheritance. I didn't realize I had this one before. Interfaces, I'll show that in a second. Instead of extending rectangle, so rather than having a superclass that binds these two, rectangle and square are separate, right? Square wraps a rectangle, or it will just define its own behavior completely separately. We recognize that in code, it actually doesn't make sense for us to do an inheritance relationship here. So either we keep them totally separate from each other, or we have a square that internally has a rectangle inside of it and handles it as a rectangle. So set side would then, like what we could have here is this be a rectangle R, and set side could then call set width and set height. So we're sort of obfuscating away the fact that set width and set height are what we're using inside of square. Or even simpler, we just defined an inside, which also works fine. My last fix, the one that I sort of got out of order there, but this one is rather than making shape into a superclass, turn it into an interface or an abstract class. So now we can get that behavioral compatibility while still using interfaces. So now if we just come back over here for a second, these would implement shape instead of extend, implement shape instead of extend, and then we'd have to implement our own get areas, whereas the properties themselves are not shared, they're not enforced. Now we could also make it an abstract class that we extend, where the get area is just an abstract method inside of an abstract class. But again, there are no fields that are shared. So making it an abstract class gives us no benefit over making it an interface. And in fact, I would almost say that it makes it probably worse, because an abstract class would allow someone else to come along and define shared fields in a way that we probably don't want. So here we can see that we could potentially do an extend shape where each one has its own information. So like this one has its width height, this one has its inside, this one has its double radius. But And then here's our abstract class, as I was just mentioning, right? Where potentially we have these sort of internal variables that we can hide away and then the abstract get area. But why, right? Yagni. We don't really need this. This is going to introduce additional complexity. It's going to allow people to add stuff like more fields to our abstract class that maybe we don't want. The interface defines behaviors, right? That's typically how we use our interfaces. And LSP is about behavioral compatibility. So it just makes a lot more sense for us to be solving LSP violations using interfaces over abstract classes, right? All of a sudden, if we wanted to add in circles or triangles, what's going to happen, right? So what if you know you're never going to need them? So even in a rectangle only world, as we saw, squares don't behave like rectangles. If we have to override our setters or rely on a width and height being independent from each other, that's not a rectangle. That's still going to be the LSP trap, right? So even if you said to me, okay, I really want to use an abstract class, I still want to be able to set my width and height potentially independently. The reality is, a circle, a triangle, a square, they are not rectangles. So it just doesn't make sense to do that. And if all we're defining is abstract methods, it should be an interface, right? So even though Yagni says don't design for shapes you don't have, LSP is going to tell us don't lie about the shapes that you do have. All right, so since we went through quite a few different fixes for this one, it's a little bit more complicated in terms of how you might approach solving this problem compared to the single responsibility principle or the open-close principle. I did put a little table together here instead for our 4 examples that we have, right? And a reminder, just like we saw with the open-close principle, and we talked about like what is a calculator and sort of the sum of its parts, just because in real life A is a B does not mean that A always would extend B in code. It doesn't necessarily mean that it's going to be a safe thing to do. I've also put together a summary table of the 3 principles that we talked about today so that you can see the core idea for each and an example of the violation for each. So after you've sort of had an opportunity to go through this and we do the other 2 in the next video, it might be nice to put it all in one table just so that you can really get a good full picture of the different principles that we're working with and how you might accidentally violate them. Now, on your own time, I'm not going to go through all of them right now. I think that these are things that you should discuss with your peers or with GenAI or with your instructor in class. But you can read through each of these each of these scenarios and identify which principle is being violated in each, given the 3 that we know. So it will either be an S violation, an O violation, or an L violation. It won't be I or D yet. 3 scenarios written out. Not only tell yourself, like, if you're going to actually do this activity, once you've read it, I would recommend actually writing down not only what violation you think it is, but defending why you believe it's that violation, why we're violating that principle. Because some of these could potentially be categorized into more than one space. And so it's really important that you solidify your understanding of why you believe this scenario is in violation of a given principle so that you can really defend your answers, because that's really what all of this is about. You can see here that I've given you a hint along each of these scenarios to sort of help you hopefully understand what words you want to pick out from the scenario to determine which of the violations we're talking about. All right, go back into your code, and one of the most common mistakes to see or violations to see is that single responsibility principle. We very, very often find ourselves coding and we just plop it all in and it all ends up in one class. So go into your projects and look for classes that might violate that single responsibility principle first. It's the easiest one to spot. And start to think about how you might want to split them up. In the previous video, when I did my refactors, we talked about like a model view controller structure in the front end. This is often how we find ourselves requiring that sort of structure, because when you first wrote up your front end, you just put it all in one file. You just called it the login page.java or the dashboard.java. And now I'm telling you to go back and look and ask yourself, should we separate out stuff? Do we have the view and the data and the controls all being stored in one file? Probably. We can go back and we can refactor those to be more in line with our principles as we've sort of defined here. If you decide, whoa, that's going to be a huge refactor. I do not have time right now to do that full refactor. That's not great, but that's okay. Just make sure that you are making a Git ticket so that you don't lose track, and you guys can talk about it at your next meeting and brainstorm different ways to fix the issues you might come across. Because even if we don't fix our tech debt right away, it's really important that we're tracking it, we're aware of it, and that we show that we're aware of it so that we can sort of consider those tasks when we're planning our next iteration. Okay, so once you've done that, you'll have finished S, O, and L in your design principles, and I will see you in the next video where we will talk about I and D, our final two design pattern principles from Solid, and how we're going to sort of spot and fix those. Thanks, everybody, and I'll see you in the next video.